guys, this is a unit on ionic bonding. It's a very, very important unit. We're going to learn how to write formulas and name compounds, something we'll use going forward. Very, very important part of chemistry. This is day one for ionic compounds. These are different types of bonds that we're going to learn. The one that we'll be focusing on this unit is the ionic bond, but here's some of the other units, or I'm sorry, some of the other named chemical bond types that we'll talk about a little bit. Metallic bonds involve metals only. Their electrons are, the way their electrons are held is kind of strange. They're in a big sea of electrons. They kind of put all their electrons, the atoms will put their electrons in a big pool, and they'll share them. Everybody gets to share the electrons. It's in like a sea of electrons, lots of electrons just floating around everywhere. And those things we call atoms when we're talking about a metallic bond. Ionic bonds, which is what we're going to be doing this unit. Ionic bonds are made of a metal and a nonmetal. So any metal from the left-hand side of the periodic table with a nonmetal from the right-hand side of the periodic table bonded together is an ionic compound. What happens with their electrons, because electrons are the only thing that is responsible for bonding, what happens with their electrons is they get transferred. So the metal has its electrons and it transfers its valence electrons to the nonmetal, and they get bonded that way because then the metal will be positive and the nonmetal will be negative when those electrons are exchanged, and they're held together kind of like in a magnetic type attraction, but it's called an electrostatic attraction. We call ionic bonds or ionic compounds formula units. Now you're used to hearing the word molecule. Not everything is a molecule. Ionic compounds are specifically called formula units. And I know it's strange, but it's just something new that you have to learn. These are called formula units. And the last bond type that we'll learn about are covalent bonds, and we'll do that in the next unit. Covalent bonds are made of only nonmetals, so it's two nonmetals together. They don't get bonded in the same way that ionic compounds get bonded together through that electrostatic attraction. Covalent compounds share electrons. They actually, somewhat like metallic, but they pull their electrons together and they share so that they both have a total of 8 valence electrons when they share their electrons. So it's a little different type of bonding. Those are the things that we call molecules. So covalent compounds you can definitely call a molecule. Water is covalent because it's made up of hydrogen and oxygen. Both of those are nonmetal, so we call that a covalent compound. It is a molecule of water. Whereas something like sodium chloride, which is salt, sodium chloride is a formula unit. So it's a formula unit of salt and not a molecule. Kind of strange. There are 3 types of chemical bonds, the ones we just talked about, the ionic and covalent and metallic, but we will be handling ionic bonding specifically this whole unit. An ionic bond, as I said before, is an electrostatic attraction between a positive ion and a negative ion. Now, we call positive ions cations. Okay, I'm going to write this and show you. We call these cations. I know that you probably looked at that and thought, oh, she can't talk. Clearly that's a cation. No, it's not, and it makes me laugh a lot inside when you guys call it that, so don't do that. It's called a cation. So, cation, I remember cations are positive. The way that I remember cations are positive, well, if you wrote this with a lowercase t, it would look like a plus sign. So cations are positive ions. Also, another cute way to remember, I think it's a little too cute for my taste, but you know, let's see. Okay. Hopefully that doesn't look like some kind of weird, you know, maybe like a possum, but it's not a possum. Okay, so cat, right? So cat ions are positive. Yep, positive. Adorable, right? Cat ions are positive. Or you can just be like me and remember, okay, the T in the middle looks like a plus sign, so positive ions are called cations. Okay, so negative ions are called anions. So I don't really have a fun way, cute little cutesy drawing to show you, but I had a student a long time ago tell me that anion, the word anion, reminds her of the word onion, and she didn't like onions, so she thought that was negative. So I can remember an anion is negative if I remember that she didn't like onions, and onions are negative to her. So positive ions like aluminum, that is a cation. Something like fluorine, and we'll learn in a little bit why. Fluorine is a negative ion, it's actually -1. Okay, that is an anion. That is a cation. Okay, remember those two. Electron dot notation. Before we can understand how ionic bonds form, we need to talk about real quick about the octet rule and then learn how to do electron dot notation. Really simple. So the octet rule, sorry, we'll go back. I guess it's a little later on in the slide, but the octet rule, if you are in band, you know what an octet is. It's 8. It's a set of 8 numbers, or 8 notes, I guess, for you guys. So the octet rule says that atoms are going to lose, gain, or share their electrons in order to get a full set of 8. Why do they want a full set of 8? Well, because noble gases have 8 valence electrons and they're extremely stable. So once those atoms have the set of 8 valence electrons, they're going to be very stable. That's what the octet rule is. And we're going to show you next how to do electron dot notation. Super easy. So what you see here, X is just any element. Okay, it's just a symbol for an element, whichever one you pick. And then around the outside of the element's symbol, you would draw the number of valence electrons that that atom has. Represents the valence electrons. So the red dots that you see on your screen are showing that that would have 8 valence electrons. So let's say sodium. Okay, sodium on your periodic table. Where is sodium on your periodic table? Group 1. Everything in group 1 has 1 valence electron. So the Lewis dot, or the electron dot notation for sodium, is that. I know, really hard. How about nitrogen? How many valence electrons does nitrogen have? Find nitrogen. Okay, so nitrogen has 5 valence electrons. It's in group 15, 5 valence electrons. So you go 1, 2, 3, 4, 5. Okay, notice I put the first 2 up here. That happens to be because of the way that the electrons fill. Remember, we learned in electron configuration that that S block gets filled up before anything else. So we put those 2 S electrons there, and then there goes 1p, 2p, and 3p. Okay, if you remember, think back to your orbital notation also, where you drew the arrows. So that would be the electron dot notation for nitrogen. Chlorine. The electron dot notation for chlorine. Well, how many valence electrons does it have? It's in group 17, so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. There's the electron dot for chlorine. So pretty simple, easy concept. So there's our octet rule. Octet rule says that atoms are going to lose, gain, or share valence electrons in order to get that full set of 8 valence electrons. 8 is awesome. 8 is great. That's what they want. That's what every atom wants to try to get. Is 8 valence electrons. Valence refers to the outer electrons in the atom only. Anything underneath that valence, that outside energy level, is a core electron. Okay, so the outside energy level houses the valence electrons. These are the electrons in the outer shell of the atom, and it's also where they're in the highest energy level. So for electron dot notation, we'd like you guys to go ahead and draw on your periodic table, do the electron dot, and you can pause me and draw the dots in for at least the first couple of rows, first 2 or 3 rows. We want to do them just for the A group elements. Now, what are the A group elements? Well, if you look on your periodic table, let me pull out one. No, that one doesn't have it. There we go, that periodic table. So the A group elements, if you look really close, are, you'll see 1A, 2A. Down here, not 2, it's B. They're B groups. The transition metals are the B group elements. Remember, they act bad. Remember when we had to do electron configuration? They're really difficult to do. So just the representative elements, which is group 1, group 2, 3A, 4A, 5A, 6A, 7A, 8A. Okay, just the A groups. The A groups are considered representative. And I'd like you to go ahead and draw the electron dot for the representatives. So in that first group, we'll start out with lithium, 1 valence electron, beryllium, 2, And we skip all the way over. Boron has 3. Then carbon has 4. Then nitrogen has 5. You're not going to be able to see that. Oxygen 6, and I'm running out of space. And then all the way at the end is neon. You're just going to have to be okay with the fact my neon's in the wrong spot. Okay, so draw the electron dot notation for at least the first couple of rows, just to kind of get yourself used to it. And again, it's only the A groups, not the B groups. The B groups are the transition metals. Okay, you can pause me and do that. Okay, so an exception. When you labeled your periodic table, you may not have known what to do with helium. Helium does not have A valence electrons. Helium has 2, but since it's in that S sublevel, only 2 electrons fit in there. So when helium has 2 electrons, it's full. It's considered to be a noble gas because it has all the electrons that it can possibly hold in its valence shell. So we showed them as a pair. Atoms which have a full set of valence electrons are very stable like those noble gases. So that's what all these atoms are trying to do. Remember, Octet Rule, they're trying to lose, gain, or share electrons in order to get that full set of 8. Please skip the transition metals. All right, so how does an ionic bond form? Ionic bonds involve the transfer of electrons from a metal to a nonmetal. Here's the bell, sorry about that. They do this so that each will obey the Octet Rule. Okay, that sounds kind of strange. If one of them's given away and one of them's taken, one of them's going to be missing electron. Well, it's not. It actually works out great. The simplest ratio of ions represented in an ionic compound is called a formula unit. Here's a formula unit of sodium chloride. Here, I'm going to draw for you if I can keep my pen. So sodium will have in its let's see, 2. I'm going to draw the 4 model for you. And then I'll easily be able to show you what happens and why this actually works. I'll give you 2 different colors. So we got sodium chloride up there. Chlorine. S4 model. One more. Okay, so here's what I've drawn. I've drawn sodium chloride. Okay, there we go. There we go, sodium and chlorine. What you notice here for sodium, it has 1 valence electron. Okay, if sodium gets rid of that 1 valence electron, look what happens underneath. There are 8 electrons underneath in the next energy level. So sodium will have a full valence shell when it gets rid of that 1 outside electron. So it's going to do that. Well, over here, chlorine has 7 valence electrons. It is dying to get 1 more. So it will take sodium's 1 valence electron, and it will have an outer energy level with 8 electrons. So that electron will go over to here, go right there. Okay, so it'll look like that. Sodium will have a full energy level underneath that 1 that it got rid of. And chlorine will now have a full outer energy level also. So when the transfer occurs going from the metal to the nonmetal, from sodium to chlorine, both of them will have their full valence shell. And that electrostatic attraction that happens is because sodium now has a +1 charge. Why does it have a +1 charge? Well, sodium had 11 protons. Look at me right upside down. It has 11 protons and 11 electrons. Okay, it did have that, right? But then you got rid of one of those electrons. I got rid of one of those electrons and sent it over here to chlorine, which then gave me 10 electrons. Look at the difference in the pluses and the minuses here. There's 1 more positive charge than negative charge. That's why sodium will end up with a +1 charge. Okay? Chlorine over here has an extra electron. Chlorine had 17 protons and 17 electrons. Count. It did. It had 17. So what happened? Sodium gave it 1 extra electron. So no longer does sodium or chlorine have 17. Now has 18 electrons. Look at the difference in the charges here. Has one extra negative charge. That's why chlorine has, yes, you guessed it, a -1 charge. Okay? It's the electrostatic attraction between the positive and the negative charged ions that cause them to stick together and bond. Okay? This is an ionic bond. This is the way an ionic bond works. And it works between those metals and nonmetals. Sodium chloride. So sodium chloride is table salt. It's the most famous salt of all, of course. But the thing is, any ionic compound can be considered or can be called a salt. It's okay to call them a salt. Now, you wouldn't want to put some of those ionic compounds on your food. That would be gross. They would be nasty and you would die. But sodium chloride is a salt that you put on your food. It's the salt that you put, like the table salt. The outer electron of sodium gets transferred to chlorine, just like I showed you. And then they're oppositely charged and they attract one another. The electrostatic attraction occurs. Okay, so here's another example. I'll erase here. Calcium fluoride. So, do a couple different colors. So we'll have calcium here, and we'll have fluorine over here. Fluorine. Okay, so I'll draw some Bohr models. It's going to take me a second because calcium's a little bit bigger. You know, you can fast forward through when I'm drawing these, right? You know, you can do that. That's the benefit of having me virtually. You can fast forward through what you don't feel like waiting on. Otherwise, you'd be in my classroom having to wait on me to do this. There's calcium, and I have to draw fluorine. Alright, there we go. Calcium and fluorine. Okay, so what's going to happen here? Well, this one's going to take a little different turn for you. Let me get a different marker. This one's going to be a little bit different. So, calcium has 2 valence electrons that it wants to get rid of, because once it does, underneath it has 8 valence electrons. Fluorine is very close to 8. It has 7 valence electrons. So, calcium is going to give up one of its valence electrons. It's going to go over here to fluorine. So it'll look like that. Okay, so here's the problem. You can't have leftovers. That's not okay. The whole purpose was to get 8 valence electrons. Now it's even worse because it's got 1. So what do you think is going to happen? Well, if you're looking at the slide, you know what's going to happen. Another fluorine's going to come along and take that other electron. Well, it would be neat if my Bohr models were similar. Okay, so there is my next fluorine atom. So what's going to happen is this other electron from calcium is going to go right down there and park over there. So that's how you get rid of the 2 electrons. They go to 2 fluorines. Okay, calcium gets rid of or loses its 2 valence electrons to 2 fluorines. So calcium will have a +2 charge because it got rid of 2 electrons. Fluorine will still have a -1 charge. Okay, but there were 2 fluorines, right? So, all right. So, do you think you can write the formula for calcium fluoride? Think logically. Can you do that? It takes 1 calcium and 2 fluorines to make an ionic compound, calcium fluoride. Okay, for all the electrons to be handled, it takes 1 calcium and 2 fluorines. The formula for calcium fluoride is CaF2, because it takes 1 calcium, 2 fluorines. Okay. All right, metals almost always lose their outer electrons, and they form those positive cations because cations are positive. Sodium will form the sodium with a +1 charge because it loses 1 electron. Calcium's in group 2. It has 2 valence electrons. It's going to lose 2 electrons. Aluminum is in group 13. It has 3 valence electrons. It's going to lose 3. So how do you know if they're going to gain or lose? Well, metals lose electrons. Nonmetals gain electrons. Also, what's happening in those groups is the atoms are trying to do whatever takes the least amount of work to get to the 8 valence electrons. So it's easier for aluminum to lose its 3 valence electrons than it is for it to go hustle 5. That's a lot more work. So it just loses those 3 electrons, those 3 valence electrons. Each time the metal loses its outside valence electrons, it'll have a full energy level below. So that's the whole purpose in the metals doing that. Nonmetals will form anions. They'll form those negative ions because they always gain electrons. If there are atoms that have 5, 6, or 7 valence electrons, it's easier to gain 3 or 2 or 1 electron than it is for it to go cut these and find more. It's just a big mess. So the least amount of work would be for the nonmetals to gain the electrons. Each time the nonmetals gain electrons, they'll have 8 electrons in their outer energy level. Okay, so calcium, if we fill in this chart, calcium is what? A metal or a nonmetal? It's on the left-hand side of your periodic table, so it's a metal. How many valence electrons does it have? Well, if you look in its group, group 2 has 2 valence electrons. It has 2 valence electrons, so it's easier to lose those 2 electrons. So it's going to lose 2 electrons, and it will have a +2 charge. So calcium is a metal, and it has 2 valence electrons, and it's going to lose the 2 electrons, and it will have a +2 charge. So in that first column underneath calcium, that's what you should see. That's what you should do. All right, bromine. Bromine is a nonmetal. It's way over on the other side of the periodic table. Bromine is a nonmetal, so it's a nonmetal. How many valence electrons? Well, it's in group 17, so it has 7 valence electrons. Is it going to gain or lose? It's going to gain electrons. It's going to gain 1 electron, because when it does, it'll have 8. Okay, its charge will be -1. Now, you're just going to have to get used to the plus-minus thing. Okay, it gives kids a lot of trouble in the beginning. All right, when you're losing, you're positive. When you're gaining, you're negative. So think about it when Miss O'Brien steps on the bathroom scale. If I lose, I'm pretty good. I'm positive about that. If I gain, not so positive about that. Okay, that's one way to remember it. Okay, so finish filling that in for aluminum and sulfur. Aluminum is a metal, has 3 valence electrons. It is going to lose them because it's so closer. It's easier for it to lose those 3 and have that full valence shell underneath. It's going to have a +3 charge. Sulfur is a nonmetal, has 6 valence electrons, way easier for it to gain 2 of them. So it gains 2 electrons, has a -2 charge. Oxidation numbers. So oxidation numbers are assigned to an element, and it represents the number of electrons that are lost or gained when they form a bond. When chlorine gains 1 electron, it forms the Cl- -1 ion. When aluminum loses 3 electrons, it forms the Al +3 ion. Problem is, the majority of elements can have lots of different oxidation numbers. Okay, that can be a problem for us. It's not exactly right with the groups, so and they can have more than 1. So what we're going to do is give you a set of rules that we want you to use. Okay, so all elements in their free state have an oxidation number of 0. Okay, free state means that it's on the periodic table, doesn't have a plus or a minus next to it. So sodium, in its free state, has a 0, has an oxidation number of 0. If you do not see a charge up here next to it, it's in its free state, and it has an oxidation number of 0. All diatomic molecules have, in their free state, have an oxidation number of 0. So diatomic molecules are molecules that can't exist alone. Okay, they form the word Brinkelhoff. And if you were in my classroom, you would see there's a sign above my board that says Brinkelhoff. Brinkelhoff. These are the atoms on the periodic table that are diatomic. They can't be alone. They always exist in pairs. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those are the diatomic elements. And when they're in their free state, with a 2 next to them, they have an oxidation number of 0. Everything in group 1, in group 2, and the metal aluminum. Okay? They always have fixed oxidation numbers. Elements in group 1 have an oxidation number of +1 because they always lose 1 electron. Elements in group 2 have an oxidation number of +2 because they always lose 2 electrons. And aluminum only in that group, aluminum always has an oxidation number of +3 because it always loses 3 electrons. Another one of our rules, oxygen always has a -2 oxidation number, except for peroxides, and we're not to polyatomics yet. Fluorine always has an oxidation number of -1, and hydrogen almost always has an oxidation number of +1. So those are the ones that you're going to have to memorize, but we'll use those rules enough that you will. When the rules don't apply, okay, we'll get to cases where the rules don't, there's not exactly a rule for that. If there's no rule that applies, we go with this basic rule set. Group 1 has a +1, group 2 has a +2, group 3 has a +3, groups 5 will have a -3 oxidation number because it gains 3 electrons. Group 6 has a -2 oxidation number, and group 7, the halogens, has a -1 oxidation number because it gains 1 electron. So nomenclature is a way for us to name chemical compounds, writing names for these things. There are very specific rules for naming compounds. You start with the simplest type of ionic compound, a binary ionic compound. Binary just means 2 elements. Just means there's going to be 2 elements in that compound. An ionic bond is always between a metal and a nonmetal, so it's usually it could be a binary compound, could be others, but we're going to learn binary first. The way that you name a binary compound is you write the whole entire name of the metal first. Then you find the nonmetal. Okay, you write its name, but you take the ending off of it and you add IDE. Okay, so NaCl would be sodium chloride, not sodium chlorine, sodium chloride. LiBr, lithium bromide. Okay, change the ending to IDE. That last one, calcium fluoride. Only the end of the nonmetal gets changed, and it gets changed to IDE. Sometimes you'll be given the name of a compound and asked to write the chemical formula. This requires 3 pretty basic steps. You got to follow them. You'll definitely need your periodic table. Don't guess. The problem is, if you're almost right, it's wrong. Okay, there's really no in between for these. If you're almost right, it's going to be wrong. So you just have to do what we tell you to do. Okay, so step number 1, write the symbols, metal first, then the nonmetal. Okay, so we have the name aluminum oxide. So I'm going to write the symbol for aluminum and the symbol for oxygen, aluminum oxide. Above each symbol, you're going to write its oxidation number. Okay, thank goodness we learned those rules. What's aluminum's oxidation number all the time? +3. What's oxygen's oxidation number all the time? -2. You learned those 2 rules. Okay, next, you're going to add the subscript so that the overall charge is 0. So the easiest way to do that is to crisscross these. Okay, so I take the 3 and I put it down there as a subscript. And I take the 2 and I put it down there as a subscript. Okay, so it would be Al2O3. Okay, when I do this, something magical happens. The oxidation numbers add up to 0. Okay, the whole reason for these guys to be transferring electrons is so that they can be stable, like the noble gases, so that they each have 8 electrons. Well, with that stability, they'll have an oxidation number or an overall charge of 0. They'll be neutral then. Okay, so how does that happen? It's really, really simple. Let me show you. So aluminum has 3 valence electrons, and oxygen has 6 valence electrons. All right, remember that? Okay, so aluminum is going to transfer electrons. It's going to transfer 1 there and 1 there. Okay, so aluminum will have gotten rid of 2 electrons, and oxygen will be full then. Okay, well the problem is aluminum still has a leftover. So what do? Here, let me show you. Let me erase and too much mess on there for you. So aluminum, 3, and then oxygen, 6. Okay, so like that. So aluminum transfers 2 electrons, right there. Okay, oxygen is full, aluminum has a leftover. That's no bueno. So we bring along another oxygen with 6 more valence electrons. And that will take the last of aluminum's electrons. Okay, what's the problem now? I know, oxygen's missing a spot. Okay, so it only has 7 valence electrons. That's no bueno either. So we bring along, yes, you guessed it, another aluminum with 3 more electrons. So I can put that electron there. Okay, so take the second aluminum, transfer 1 of its electrons. So now both of the oxygens have 8 valence electrons, but that aluminum only has 2. So we need 1 more oxygen. And at this point, you're probably going, oh my gosh, this is going to go on forever. It's really not. It actually works out. See? Okay, look what happens. I needed 2 aluminums and 3 oxygens so that they both have enough electrons to have their full valence shell. So that's why the formula is Al2O3. Yeah? Because you have 2 aluminums and 3 oxygens. Al2O3. Okay? But it also works just by crisscrossing. Okay? If you write the oxidation number above each of those, like I've done in blue here, and you crisscross them like that, just the number, not the charge, leave the charge alone. If you crisscross them, look what you got. You have the same thing, just way less work. So how about trusting me? Okay, all you do, write the oxidation numbers above, crisscross applesauce, you're done. Okay. So we'll be going on to do some more different types of bonding. There are different types of ionic bonding, naming, and formula writing for the next unit. So rewind me, or even better, go do the homework video. That'll help you out a lot.